All right, the next part of chapter 5, we're going to start off where we left because I lost track of time and I chopped off in the middle. So we'll go back, revisit, sorry about that. Anyway, so now we've got the atom. We know Dalton discovered that there's these little particles that you can't break down. But now they actually started finding parts of it. So kind of almost 100 years after Dalton, a guy by the name of Thomson discovered that there were actually charged particles in an atom. And he did it with a cathode ray, which you can see right here. They travel in straight lines. This is a stream, like a light stream almost, but it's traveling here. And what he did was he started passing like different charges up here and he could actually deflect it. So when he put a positively charged particle here, what he found out is this was attracted to it. So he knew it had a negative charge to it. Okay, so he deflected that. And so he's the one that gets credit for discovering the negatively charged particle, which is the electron. Okay, so atoms are the smallest particle to make up all matter, but they're actually made up of smaller pieces. Okay, they have to stick together to be considered an atom. You can't just take those pieces off, but there are subatomic particles that are in an atom. Sorry about that. I thought I turned that off. Anyway, an electron is really, 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 really tiny. Okay, it's so small that they don't even calculate it in when they figure out the mass of an atom. They don't even take electrons into consideration. They're just too tiny. But it does have a charge of -1, which is important because that charge is what keeps it in the atom. You have a positively charged middle, so you have these negative charges on the outside that are attracted to it. But again, they're really, 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 really tiny. Okay, so a cathode ray, what he used, discovered electrons. Okay, that's what Thomson is given credit for. He discovered electrons. Okay, protons, okay, are also in an atom. They're the positively charged particles. So if you have 25 electrons, 25 negative charges, you need 25 positive charges. Okay. Protons are a lot heavier. You can see 1,837 times heavier than an electron. They're still not very heavy because remember, an atom's pretty tiny. But because they're so much heavier, when you're trying to figure out the mass of an atom, you do calculate the number of protons. You don't calculate the number of electrons, but you do protons. Now, when Thomson got done discovering these electrons, he made a proposed model of the atom. You can see this is a theory. And this is one of those that got thrown out because it just wasn't any good. But you see what he said was an atom is like this big glob of jelly. And it's kind of got these positively charged, and these are the electrons. The negatively charged particles are just kind of scattered throughout it. So this was his idea of what an atom looked like. Okay, Thomson proposed that the ions, these charged particles, the cations and the anions, they are made when they lose electrons or gain electrons. That part he was good on. His atom model wasn't so good, but he was smart here. Okay, and if you'll notice these guys, sodium, aluminum, these are the guys, the metals are the ones that like to get rid of their electrons. And we'll talk more about why that is, but it helps them become more stable. So if they lose electrons, they become positive and they're a cation. If they gain electrons, and again, these are going to be the nonmetals, chlorine, sodium, oxygen, all the halogens, fluorine, bromine, iodine, they pick up electrons. And so because they pick up negative charges, they become negative and they're the anions. So the metals become your cations, your positively charged, and your nonmetals become your negatively charged, your anions. And Thomson was right on with that. That's, that part of his theories were correct. Okay. All right. Another guy that discovered 1932. Okay. So not even, that long ago, a guy by the name of James Chadwick, he discovered that not only do we have, they already discovered the positive charges and the negative charges, the protons and the electrons, but he said there's something else in there that's giving it mass. And so he discovered there's actually something called neutrons, which was hard to discover because they don't have a charge, so you couldn't mess with them like Thomson did with electrons. But again, he discovered that they have these other particles. So an electron is made out of 3 different particles: protons and neutrons, which are found in the middle in the nucleus, They give the mass of an atom. And then you have the electrons, which are on the outside, and they even say they're found in an electron cloud because, you know, they just don't have much mass to them, but they do have that negative charge. Okay, so if you can't see, this says neutron right here. Sorry, guys. But we have electrons, protons, and neutrons. Electrons are negative, protons are positive, and neutrons don't have a charge. And here's the mass. And if you notice, these two guys are real similar to each other. So when you're trying to figure out the mass of an atom, what you do is you take the number of protons and the number of neutrons and add it together. Each of them have been assigned the mass unit of 1. So if something had 25 protons and 27 neutrons, you know it has a mass of 52. Okay, add those two together. The electrons are too small. Their mass doesn't figure into it. So you don't take the mass of the electrons. The charge of the electrons is really important, but the mass is just too small to use. Okay, so proton, if it's got a positive charge, is a cation. Okay, an electron would be considered an anion because it's got a negative charge. And I really did turn that off, you guys. I'm sorry. A neutron, well, if it doesn't have a positive charge, it's not a cation. If it doesn't have a negative charge, it's not an anion, so it must be none of the above. Okay, so what is the relative mass of an electron? We said it's just so small. Okay, it's not slightly larger or slightly smaller. It's a lot smaller. Okay. Okay, and there's a video, and you can go back and watch that. I'm not going to go through it. You can do it on your time. Okay. All right. So now we have this plum pudding model of Thomson. I'm checking the time, you guys. Where he said, you know, you had this big blob and it has all these electrons. Well, then this guy by the name of Rutherford, Ernest, he came along and he did some experiments. And what he did was he passed a beam through gold foil. This was his element that he worked with. Now, if it's like Thomson said, all of it should just pass right through it. But some of the beams reflected back. He's like, wait a minute. If it's just this empty space with, these randomly scattered things, that wouldn't be the case. But some of them actually got reflected back. So what he said is there's a really dense part in the middle. And he called that the nucleus. Okay, so if you look here, yeah, most of them just pass through, but some of them get slightly deflected and some of them really come back. So what he's saying is when you have these atoms, they're not just these random blobs. There's an actual dense part in the middle. So what Rutherford gets credit for is discovering the nucleus. Okay. Oh, that's really annoying, and I'm really sorry. Okay, Rutherford's experiment, he said that most alpha rays are going to pass through it, which you expect because atoms are mostly empty space. There's a lot of just empty nothing there. But because some of them reflected back, they repelled them, they must have hit something and reflected back. And that's where he came up with the nucleus. And he said it was positive because remember, electrons are negative, so the nucleus must be positive, which is what it is. Now the nucleus has two things. It has the protons and the neutrons, but remember the neutrons don't have any charge. So you have a positive middle and you have a negative outside. Okay, so he bounced back. So they, like I said, they must have encountered something very dense. So he also came up with the idea that most of the mass of an atom is in the nucleus, which makes sense because that's where the protons and neutrons are. Those are actually the only thing we use when you determine the mass of an atom is the protons and neutrons. So now this throws away the plum pudding model. And what we've got now is we've got a dense middle with like a cloud on the outside. Okay. So here's what instead, again, we have the nucleus, which is made out of the neutrons and the protons. And it's also most of the mass. Okay. If it was on a large scale, it would be super, super, super heavy. I read somewhere that if it was the size of a dime, if you dropped it, it would be so heavy, it would just like go down through Earth without, just keep going and going and going because it'd be so heavy. But again, then you have this cloud region, and this is where you find the electrons. Now, there might only be a few electrons here, but it's mostly empty space. So that's the, the atom model that we have now. Okay, a neutral atom is going to have the same number of protons and electrons. All right, so if you have 25 protons, you have 25 electrons because the charges have to equal each other. If not, then you have an ion. Okay, so an atom doesn't have a charge. If you take away electrons or you add electrons, now you have an ion, and that's something different. Okay, so the mass of an atom we talked about is protons and neutrons. We don't figure out the electrons in there. The electrons are just too small. Okay. All right. So when you look at a periodic table, the elements are all organized. And they're put in there by what they call the atomic number. Well, atomic number is the number of protons. The first periodic table, maybe I talked about this before, was organized by atomic mass, and it didn't work. It was almost perfect, but there just was some spots where it was messed up. But when you put the elements by atomic number, by the number of protons, it works perfect. Okay, so anytime you find an element, like if you find iron, its atomic number is 26. That means it has 26 protons. If you change that number, then it's no longer iron. So it has to have 26 protons. Okay, whatever the atomic number is, the number of protons, that determines what element. You can change the number of electrons. You can change the number of neutrons. But if you change the number of protons, you have a different element. Okay? Okay, so the atomic number determines the identity of the element because that's the number of protons, and that number never changes. For every element, the proton number or the atomic number determines what element you have. Okay? If you look at sodium, sodium is Na. Its atomic number is 11. So it always has 11 protons. If you change the number of protons, then you have a different element. Again, you can change the number of electrons, you can change the number of neutrons, but you can't change the number of protons. Okay? So if you're talking about an atom, then the atomic number also equals the number of electrons. Okay? Because if you have a sodium atom, it doesn't have a charge. So if you have 11 protons, you also have 11 electrons. You can change the number of electrons though, and actually sodium will give up 1 electron. So it'll go down to 10. And now it's not an atom anymore, it's an ion. Okay, so we're doing what? Potassium. If you find potassium, potassium has an atomic number of 19. Okay, that means it has 19 protons. So if it has 19 protons, it has 19 electrons. Okay, remember that the number of protons and electrons always equal each other in an atom. They have to because an atom doesn't have a charge, so your positives and negatives have to equal each other. Okay. All right. Then we also have something called isotopes. Okay, so if you take an atom and you add a neutron or you take away a neutron, it's just going to be heavier or lighter. So its mass number will be different. Okay, so again, we can change the number of electrons, we can change the number of neutrons, we can't change the number of protons. So an isotope is an element with the same number of protons but different number of neutrons. It has a different mass, and those are called isotopes. And every element has a couple. Here's the ones for hydrogen. Okay, hydrogen has no neutrons, 1 neutron, and 2 neutron. And you can see when you write it, what you do is you put the atomic mass right here, and you put the atomic numbers up here. Oh, it's on the bottom. Yeah, the mass is up here, the number's here. Sorry. If you look here, this one has 1. Well, now you have 2, 1 proton and 1 neutron, and now you have 2 neutrons and 1 proton, so it's 3. So the top is the mass. The bottom is the atomic number. That doesn't change. If you change this number, now you have a different element. Okay? So that's an isotope. We're at 14 minutes, so we're going to run out of time here. So what I'm going to do next time is I'm going to explain to you how how isotopes figure into the mass of an electron. So we're going to quit right here, and then we will pick up later. We should probably finish on the next recording. All right? Again, if you have questions, let me know. We'll talk soon.